So the activity today is to experiment with glow sticks and see how you can affect the intensity of glow stick light. So let's get stuck straight in and think about how experimentally we might be able to affect that intensity of light that's emitted by a glow stick. First of all, we'll need to think about how we actually get the glow stick to emit light in the first place. You've probably done this yourselves. You're probably aware that you have to snap the glow stick and then maybe shake it, maybe snap it a bit more. So that must suggest that there are substances that are kept apart until the snapping allows them to mix or react. So if we think of those substances as reactants that need to mix or react together to produce light, how can we make that happen quicker or slower? i.e., how can we affect the rate of the reaction? Now, hopefully you know there are a few factors that can affect the rate of a chemical reaction, but really there's only one that we could possibly use in a home environment here. And the one I'm thinking of, and hopefully you're thinking of too, is using temperature. So one of the ways that we know that will increase the rate of a reaction is to increase the temperature. So this is something that we could relatively easily look at with regards to the light intensity of a glow stick. We're going to think about resources now, and so at this point it'd be useful for you to have the worksheet available so you can follow instructions and complete various parts of the worksheet. So from the slide you can see in order to perform this experiment you're going to need access to some glow sticks and hot and cold water and ice and salt. I don't have a thermometer at home myself, so I'm going to have to modify the experiment in order to look at the higher temperature. I'm going to boil a kettle and then measure 3/4 of a pint of boiling water and top that up to a pint with cold water and use that as my higher temperature. Please be careful using a kettle. Definitely don't use a kettle in a dark room. You're going to need a dark room or a darkened room later to visualise the glow sticks in, so don't use the kettle in the dark. But before we actually get started on the experiment and looking at different temperatures, how about we first take a look at the glow stick, just in the light, and just visually, let's have a look at the structure of the glow stick and see if we can observe anything interesting. So at this point, I'm going to pause so you can check out my first video where I have a look at the glow stick in the light, and I will share what I see with you. So before we start our experiments in dark rooms, snapping the glow sticks, it's a good idea to just check out what they look like in daylight and see whether we can see what the structures of the glow stick are. I mean, in terms of observations, first of all, I guess it's fairly obvious that we have a variety of colours here, ranging from a sort of a pale yellow, stroke green, orange, pink, maybe sort of red, and there is also what appears to be a colourless glow stick. So we're going to think about how these work in a minute, so it's a good idea to sort of pick one up and have a real look at it to see whether you can see anything else. So I don't know whether you can see, but I can certainly see at the, if I sort of rotate one so that I've got a bit of a gap at one end in terms of what looks like the yellow liquid, you can see initially where my fingernail is there's a couple of bubbles within this yellow liquid, but also to the right of it, can you see that there is an inner tube? You can see this sort of black inner tube running through, although it isn't actually black, but there is an inner tube running all the way through, and if you look closely, it's difficult to tell via me filming, and it's better probably if you have a look at this in real life. There's also a liquid within that tube, the inner tube itself. So you've got this plastic outer tube, and then suspended within it is an inner tube, separated. The two tubes are separated by this liquid, in this case the coloured yellow liquid. But then there's an inner tube that looks black at the moment, just by contrast, and that is containing another liquid that you may or may not be able to see. Okay, so hopefully you've had a look at your glow stick, or you've had a look at my video, and essentially you've got a long plastic tube which has an inner tube and they are separated by some kind of liquid, and that might be coloured depending on what glow stick you're using. And you might see some bubbles as you rotate the glow stick around as the liquid moves back and forth. Okay, so now I'm going to pause again so you can watch the second video, or you can pause the PowerPoint yourself to watch the second video showing my experimental setup and the observations that I made. Again, use the worksheet to help you. There are various questions and instructions throughout. Also, it would be great if you could have a think about the answers to the question on this slide. So why use glow sticks of the same colour? Why add salt to the water containing ice? Why not use water hotter than 70 degrees? Okay, so we're going to start the experiment. But first of all, I'm actually standing in a room that's not particularly dark. I've got a light on and I'm going to switch it off in a bit. But I just thought I'd orientate you around what I'm looking at so you understand the difference in what's in the glasses in front of you. So if we go to the left, the one with the glow stick in, that's just an empty glass. If we then look at the next glass to the right of the glow stick, you can see there's some ice floating in the top there. So that's going to represent our colder temperature, and I've also put salt in there, and I've asked you a question, haven't I, as to what would be the effect of salt on that cold water. Then next to the glass with the ice in, it's just room temperature water. I didn't put that in the worksheet, but I thought it would be a good idea to have room temperature water in there as well. Then to the right, I've got some hot water. Now, unfortunately, I can't tell you the temperature of that. I can just tell you that it is much hotter, subjectively feeling it, than any of the others. I don't have a thermometer at home, so this experiment is not going to be precise, but it's going to give you an idea about what happens to a glow stick at colder and relatively warmer and hotter temperatures. So the first thing I want you to do is feel your glow stick. So just take a glow stick that hasn't been used yet and just feel it. Get a sense of the temperature of that glow stick, and it shouldn't really feel hot, it shouldn't really feel colder, you shouldn't really get a sense of any particular strange temperature going on here, or strange difference relative to the room temperature. And then what you can do is actually sacrifice one at the beginning, just so that we can feel it, to see whether we can feel whether the glow stick is getting warmer or colder. So we're looking for endothermic or exothermic type reactions. So if you feel it going colder, can you remember what that reaction would be? So if it feels colder, that's an endothermic reaction. If it feels hotter, that's an exothermic reaction. Okay, so I'm going to crack one in front of you now, and we're going to observe what it looks like, and also feel whether or not we can sense any temperature changes. So I'm now going to switch off the light. And if I take my glow stick in front of the camera here, I'm just going to crack it, and I'm just going to let you listen. So hopefully you heard a lot of that sort of cracking sound, and that's the inner tube, which is actually made of glass, and that's cracking. So that glass is cracking inside, and you can see there's sort of like different pockets of high intensity colour and not so high intensity colour. So you might want to give your glow stick a bit of a flick. So what you're doing here is you're mixing some chemicals. There are chemicals in the inner tube and there are chemicals in the outer tube where you originally saw the colour. So now we're getting more of a homogeneous colour, aren't we? Intensity of colour. Okay, I'm feeling the tube as well with my hand. And I can't feel, if I'm honest, I can't feel any particular difference. I can't tell you, oh, that feels much colder or much warmer than it did before I cracked it. So not sure about that one. I wonder what you thought. Okay, so now what we're going to do is we're going to take 4 of the same colour. And the question is, why would you use the same colour? There are lots of lovely different colours. Why don't we use different colours? So have a think about why we use the same colour. And I'm going to remove the glow stick that I've originally got in there because I want to start this experiment all at the same time with my 4 glow sticks. You may have 3. And what I'm going to do is I'm going to slap them all at the same time. And I want you to be thinking, why? Why should I do it all at the same time? I'm trying to give them a flick so again I can get that intensity of colour throughout all of them. And then I'm going to pop 1 in each condition. And let's see whether we can see any differences. So if we again remember that the one on the left is just the glow stick in air, the one next to it is the glow stick in ice, and we've just got room temperature glow stick in water, room temperature water, and then we've got the glow stick in the hotter water, so probably above 70 degrees, but not more than 80 degrees. That could have an effect, and that's another question I asked you, I think, on the PowerPoint slides. So already, hopefully, you can see that there's a difference in intensity. And I'm just wiping off the condensation on the outside of these glasses. I'm going to shut my door a bit more in the hope that we can see more of a difference here. So what's standing out to me big time is the glass on the right here with the hot water. The intensity there is much, much greater than any of the others. And I would argue that the intensity in the one with ice is much less than the one with the hot water, but less than the room temperature ones as well. But it's not hugely apparent from these two. The other thing you can do is have a look at the moment, the 3 glasses on the right. Some of the glow stick is suspended in the water and some is actually just suspended in the air. So that's quite a good control experiment. You can see what's happening in and out of each condition. So you can see above the glow stick with the hot water, it's less intense, isn't it? Because it's not in that hot water, it's just in room temperature air. So you could say that all of those have got their own internal controls. The other thing that you, if you get really close to these, might be able to see are bubbles. And it might be something that you might want to observe maybe more at the start of the experiment, but sometimes you can see sort of bubbles rising. It's very difficult for me to show you this with my camera, but if you get close you might be able to see these, and it would be really interesting to actually compare the rate of bubble formation for each of these conditions, and that's something that I'd like you to think about a little bit further. So there we go. There's our glow stick experiment done for now, and I'm sure that's given you a lot of things to think about and lots of questions to be able to answer. Okay, so before we move on to the table questions in the worksheet after you've done the experiments, let's go back to the questions on the slides. So the first one, why use glow sticks of the same colour? Well, hopefully you recognise that was a way of looking after our control variables. So the colour may affect the results. So keeping it the same, i.e. using that as a control variable, means we are trying to just observe the effect of change in the temperature and not the effect of colour on light emission. The second question was, why did I add salt to the water containing the ice? This is something you might want to research a bit further, but this allows the water, the salty water, to reach temperatures lower than the freezing point of pure water, so I can get that temperature right down. The next question was, why use water no hotter than 70 degrees C? So some of you might have been thinking, well, maybe that's something to do with safety, and yes, definitely a safety element there, but actually the plastic of the glow stick will possibly dissolve and the inner chemicals may leak out. And if you have a glow stick, say in a plastic cup, the chemicals that leak out might actually cause the plastic in the cup to dissolve too. Okay, if we now go on to the observations and results, I'm hoping at this point that you would have completed the experiments as per the worksheet. If you need more time, now will be a time to pause the slides before we go on to answering the questions. So let's go through each question and compare answers. So first of all, what does the glow stick look like in the light before the experiment? Well, as I said earlier, I mentioned it's a plastic tube, but it's also flexible, isn't it? It's got a bit of a bend to it, and with an inner glass tube. Although I suppose you couldn't necessarily observe that it was glass, but it is in fact glass. But when you cracked it, that might have given you a suggestion that maybe inside was something like glass. It says, compare the temperature of the glow stick before and after snapping it. Well, I don't know about you, but I found it very difficult to tell whether there was any difference just via touching the glow stick. So I don't know whether it's an exothermic or endothermic reaction at this point. Consideration number 3, then compare the light intensity of each glow stick and how quickly changes occur in each. So I think it was obvious that with the hot water, the intensity was much brighter than the other temperatures. And it reached at high intensity quite quickly, didn't it? In terms of the cold ice solution, well, we never really saw in the video it reaching the same level of intensity as the glow stick in the hot water, but maybe over time, if we'd given it more time, we might have seen it increase in intensity. It says compare the rate of bubble formation in the 3 glow sticks. Well, if you had held your glow sticks really much closer than I was able to show you via the video, you would have seen bubbles appearing, and with the hotter glow stick, you would have probably got a sense, if you looked at the hot and the cold glow sticks in direct comparison, that the rate, so how many bubbles formed per time, was much quicker in the hot condition rather than the cold. The last question, what happens when you remove the sticks from the hot and cold water? Well, I didn't show you that on the video, but hopefully you did that one yourself. And what you would have noticed with time was that with the hot condition, removing the glow stick from that, the intensity decreases slowly. And with the cold, again, the intensity increases slowly as it equilibrates to room temperatures. So if you haven't done that already, that could be something you have a look at also. So let's look now at the actual science behind all this. What is a glow stick actually made of? Well, if you look at the diagram on this slide on the left, and actually you would have seen this yourself firsthand by looking at a glow stick, then the glow stick is a plastic tube with a thin tube running through the middle of it. You can see that they both contain liquids. Well, the inner tube, that might have been tricky to see. Maybe you did, maybe you didn't. You might be able to see the liquid has a pale colour too, and that was certainly evident for the yellow, the orange and the pink and red. Some of you might have tried maybe what looked like a colourless one at the beginning, and that actually went a beautiful blue colour, but it was very difficult to tell that in advance what colour it was going to become. Okay, so let's have a think now about that inner tube and the outer tube. The inner tube has a chemical called hydrogen peroxide in it, H2O2. You might have come across that before. It's kept separate from the other 2 components. And it's kept separate via a liquid. And that liquid contains an ester and a dye. You might remember, or you might have done, you might not have done some organic chemistry where you've looked at esters being a family within the organic chemistry part of your course. But don't worry about the names of all these substances on the slide, just regard them as reactants in a chemical reaction. So once you snap or you crack the glow stick, the inner tube releases the hydrogen peroxide. This then reacts with the ester to form what's called a phenol and a dione. The dione then goes on to react. It's actually quite unstable, and it decomposes to form carbon dioxide, and it also releases energy at this point. And that energy is absorbed by electrons in the molecules of the dye. And they subsequently fall back to their ground state, losing the excess energy in the form of light. And that's what we see. We see this chemiluminescence. So with time, the electrons fall back down to their normal levels and the glow stick gradually dims. And this is an example of an irreversible reaction. So you cannot reuse a glow stick, but you can slow it down by putting it in a freezer. If we then look at the next slide, this is an infographic. It's taken from a website called Compound Chemistry, which I've found to be an excellent site to find all sorts of graphics relating to the chemistry you study at school, but also it's a great way of finding out about chemistry's involvement in everyday objects and reactions. This diagram in particular shows the different types of dyes or molecules involved in creating the different colours that we see in glow sticks. Again, you could pause here if you wanted to continue doing some questions on the worksheet, and because I'm going to go through those questions in the next slides. Okay, so if we have a look at the first two questions, the first question was in step 1, all 3 glow sticks were activated at the same time. Why was it necessary to do this? And the second question was, why was it necessary to use 3 glow sticks of the same colour? Well, hopefully both these questions you were thinking of control variables. So both questions were targeting your awareness of using control variables to ensure this is a fair test. If we look at the questions 3 and 4, so question 3, is the light intensity of the 3 glow sticks different at different temperatures? Explain. And do bubbles form in the glow sticks at different rates at different temperatures? And again, explain. So both questions here were targeting your knowledge of rates of reaction. So the light intensity and the rate of bubbles will be greater at the higher temperature. And in terms of an explanation for all this, so increased temperature, you will remember from your rates of reaction course, causes disproportionately large increases in the number of high energy collisions. Only these collisions, so collisions that possess at least the activation energy, will result in reactions. And you can see from the equation on the slide here that when the dione reacts with the dye, it forms CO2 gas. So that's probably what we're looking at in terms of the bubbles. Okay, so question 5 and 6. When do bubbles stop forming in a glow stick and why? And when does a glow stick stop glowing? And why do you think this is? So again, both questions were targeting your knowledge of rates of reaction and reversible and irreversible reactions. So as I said before, this is an irreversible reaction. So the reaction slows down and stops as and when all the reactants are used up. So no more products can form. And therefore, no more, we do not see that emission of light. It did. Question 7, if you keep 3 activated glow sticks for several hours at different temperatures, and then allow them to come to room temperature, how do you think the light intensities would compare? And explain your reasoning. So again, we're targeting rates of reaction. So if the glow stick that was originally in the hot water is put into, say, cold water or room temperature, the light intensity of the bubbles will decrease. Think about the kinetic energy of the reactants is going to decrease, so there's going to be less collisions, less particles can overcome minimum activation energy, etc. And then the opposite then for the condition whereby you're taking a glow stick from a cold condition to a hot condition. What do you think would happen though if you left them all at room temperature for another hour? So if you took the hot from the hot condition, the glow stick in the hot condition, laid it on a bench, and the glow stick from the cold condition, laid it on a bench, and just let them both be for a couple of hours, what do you think you would see? Well, I would suggest that they would all display the same light intensity. They would all sort of equilibrate to that room temperature and therefore have the same rate of reaction. Okay, so now that we've done some experiments and we've had a think about what those experiments mean, it's always a good time, isn't it, to reflect. Maybe on the way that we did the experiment and how we can improve the experimental design, and maybe think of other experiments that could take our learning further and answer maybe some questions that we didn't feel were answered during our investigation. So let's just start with the observations first. we were observing light intensity and bubble formation. Bubble formation was quite tricky, wasn't it, to see? The way we did it was via subjective comparison. So we were just looking at the glow sticks at room temperature and cold and hot water situations. So this is more of a qualitative observation. We're not measuring any numbers. It's not quantitative. So maybe making it more quantitative and taking some kind of quantitative measure is more optimal, because then we could make more comparisons and it's much easier to share data with other people then. So the question is then, how could we make the equipment or the experiment and our observations more quantitative? So we could have used more specialist equipment, obviously difficult at home. So there are pieces of equipment that can measure light intensity directly, so light meters or photometers. We could have also counted bubbles released during a certain time, so we could make it more quantitative. So say count the number of bubbles observed in 30 seconds for each of the conditions, and therefore we'd be able to have a relative rate of reaction that way. In terms of more experiments, well, glow sticks come in many different colours, and remember at the beginning we talked about the fact that we had to use the same colour because we didn't want colour to be a factor that could cause difference in light intensities. And the reason for that is because actually there is research that shows that there is a difference in light intensity between different colours. And green and yellow are typically the brightest intensities, followed by orange, and red apparently has the shortest sort of shelf life, or the smallest intensity. So it could have been interesting to look at maybe one condition, so one temperature, and then look at different coloured glow sticks and see whether there are any differences, and maybe whether or not a particular coloured glow stick lasted longer. So leave it for a day, 2 days, a week, etc., and then just see which one lasts the longest. So in this PowerPoint, and there are notes at the bottom where in this particular one there's a link, and you might find that quite interesting, because some people have done experiments where when they've heated the glow sticks to higher temperatures, they've actually seen colour changes in the same glow stick. So not just an increase in intensity, but at a certain point the actual colour changes. So that sounds like a very interesting experiment to carry out, if it can be done safely, of course. And maybe you've got some other suggestions for other experiments you could do with glow sticks. So I thought I'd give you a bit of a problem to solve for me. So some troubleshooting here. So a few years ago I bought many glow sticks and then didn't use them. And when I recently went to use them, they didn't work. Why do you think that might be? So if you look at the slide, what I've done is I've put the science of the reaction, so you can think about that, but you can also maybe think about the materials that the glow stick is made from. So let me give you a bit more context. These glow sticks had been kept for more than 2 years. There didn't appear to be any damage to the plastic tube of each one or the inner glass one. So it didn't look like the sticks had been able to sort of mix the reactants. I did think though, in that first equation, if you have a look, there's hydrogen peroxide in there. And you've probably done quite a few experiments if you've done rates of reactions with hydrogen peroxide and catalysts maybe, because hydrogen peroxide does actually decompose quite slowly into water and oxygen. And one of the ways that students look at changing factors in rates of reaction is by adding catalysts, and this is a classic sort of experiment. So I did wonder maybe with time that hydrogen peroxide had decomposed, and therefore when I did snap the glow sticks, they didn't actually work because the hydrogen peroxide had already decomposed into water and oxygen. But I also read that some of these glow sticks can actually absorb water, and so that could be another way in which basically the reactants become diluted, and compromised, and therefore when I went to use it a couple of years later, again the reactants, the concentrations weren't high enough to react. But of course some of these glow sticks are used in diving and swimming and things like that, so it must depend on the manufacturer of the glow stick. But I wonder if you have any other ideas why my glow sticks didn't work. Then I've touched just a little while ago on the fact that glow sticks can be used for diving. So applications then, why do people use glow sticks other than for fun? And can you think of any problems they may have based on your results that you've just seen today? So I don't know whether you know, but glow sticks were originally designed by the military. And in fact, glow sticks are the only light source considered to be safe for use after natural disasters and in emergency situations. Because if you think about it, they don't need electricity and they don't produce any sparks, making them the only light source in explosive situations. They can also be used as a kind of a safety tool in diving or mountaineering or night sports. So let's think about what potential problems then. What do you think the problems might be if they were used, say, for example, in mountain rescue in very cold, snowy environments? So based on the experiments we did today, there would be advantages and disadvantages, wouldn't there? On the one hand, a lower temperature will increase the life of the glow stick, so it would last longer. But on the other hand, the intensity of the light might be suboptimal compared with higher temperatures. So let's look at glow sticks again, thinking about the materials involved in the glow stick themselves. And there are two sort of interesting materials I thought that we could discuss. So one is the fact that glow sticks, the plastic, when you think of plastic, you probably think of polymers. And that glow stick is made from plastic, so it's made of polymers. It's quite flexible, isn't it? So that actually is because the polymer contains something called a plasticizer. So plasticizers decrease the attraction between polymer chains. You can see that on the diagram on the slide. And it makes the plastic more flexible. But it also means that if a glow stick leaks onto anything plastic, it can liquefy it. You probably are aware of some materials that contain plasticizers. So for example, PVC, polyvinyl chloride, is a polymer that doesn't contain plasticizer, but UPVC, and think about window frames perhaps, they refer, oh sorry, I should have said that plasticizers, PVC does contain plasticizers, but UPVC, and that would make more sense, wouldn't it? Because windows, you want them to be quite stable and not flexible. So UPVC refers to unplasticized PVC. So the other material that I considered was the use of chemiluminescence in material science terms. So if you have a look at the pictures on the right of the polymer picture, what that's meant to be showing, especially the one on the far right, is bioluminescence. And that's the sort of natural version of chemiluminescence. And I thought it was quite interesting because due to the COVID-19 pandemic, the picture on the right actually shows an increase in bioluminescence as compared with times without COVID-19. And they believe that's because there's less people on the beaches. This is a beach on the Pacific coast of America. And they believe that because there are less people there, there's less interference and less disturbance by people, and the organisms that produce that bioluminescence are able to propagate, so things like algae and plankton. But thinking of things synthetically and in terms of material science, chemiluminescence has been used in nanotechnology, and has been used extensively in sort of analytical methods of chemistry. So anything that requires some kind of detection. And I suppose one way of finding a context there is that you've probably heard of luminol in forensic science. So that's used to detect blood and other things. Okay, so I hope you've enjoyed the activity. It's given you a lot to think about in terms of how glow sticks work and how you can affect the light intensity they emit by varying the temperature. Whilst performing the experiment, I hope you appreciated how limited we were with the experimental design, only able to make crude, subjective observations. But nonetheless, that did allow us to see that temperature does affect light intensity. I also hope you've enjoyed learning about how the chemiluminescence is generated within the glow stick and some interesting points about the materials the glow stick is made from. It would be marvellous if this activity has got you thinking about other experiments you could possibly do too. Maybe something that is a bit more quantitative rather than qualitative. Thank you so much for taking part in this activity. Keep thinking like a scientist and make sure you have fun with science too.